Welcome you all. Today we will discuss about the artificial neural network. So what is meant by artificial neural network means, example, if I have taken, our brain can perform enormous activities, okay, and there are total our brain, if I am taking neurons in our brain, it's around 80 billion, okay. 80 billion neurons are interconnected each other, and these neurons are store the energy and store the information. It can perform different tasks. So if these brain functions, if we are mapping into our practical for the practical applications, so this can be suitable that the artificial neural network will perform the brain mapping into the some mathematical functions and for different applications. So here today we will discuss about the simple single neuron and what are the inputs and its parameters, and what are the different activation functions and loss functions will be discussed in the class. So before going to this one, let us see. So this is the single neuron, the architecture. This is called as a, if I am taking this one is the synapse connection, and these are the example that this side is the input to the our brain cell. This is called as a cell, okay. It's our center of the neuron. It can perform the main mathematical functions over here. That is whatever the decisions are, whatever the inputs are arrived into this cell, it can perform and give the output. So this is the synapse connections, this yellow color, and which is connected to the adjacent neurons, and this is also called as dendrites. If I am taking this one input to this neuron, it is simply dendrites. So these dendrites will receive the signal, and these all dendrites will transfer the signal to the main nucleus. So this nucleus can perform the operation and it will give a output. This output will be transferred to the some other neurons by using these axon terminals. This is called as axon terminals, okay. So these axon terminals are at the end, which is connected to the some other neurons, okay. Like this, every neuron can share the information with the other neurons, and it will store the some information. It will process the outputs, and some for the different applications it can perform different tasks. So continuously it will these neurons will be activated continuously. It will give a outputs, okay. So this is the architecture of the neuron. So here, if I am mapping to this neuron into our neural network, that is artificial neural network, which is we can call it as a perceptron learning single neuron. So this one I am taking as a our nucleus, okay. So here just we are summing the whatever we are receiving the inputs, okay. Now there is a one input. I am taking only two inputs over here, okay. There are in practical in the sense our brain neuron, it is around from 1 to 10,000 inputs will be inputs are to the single neuron. That is very highly complex. So that highly complex, it is now practically very impossible to implement, okay. But the researchers are trying to completely map the brain functions in the generative AI some future applications. So here I am taking only two inputs. First one is the, let us take x1 and another one is the x2, and this one is the and output is simply, we can take the one more. There is some activation function. So I am writing AF, and it will give the some output. And here two things are left, that is a weight W1 and W2, and one more, it is a bias B. So this is the complete architecture of the single neuron. It having n number of inputs with associated weights plus function, that is a plus bias, it will be summed up. So if I am taking this one is a y, that is sum. So y equal to x1 w1 plus x2 w2 plus your bias is the b, okay. So these are the mathematical function at this one, okay. What is the w1 and w2, okay. These are called weights, w1 and w2 called weights, okay. What it does, what is the operation of these weights will tell you the relationship between the output and input, how much it has a relationship. If weight is uh, highly rated, that is a high value, then there is a good relation between the output to the input. If it is a weights are very small, then you no need to care about the inputs. Example, W1 is equal to 0.7 or 0.8. It is highly related with the this feature. If I am taking x1 and x2 are some features, then we have to give a more importance to this feature. If W2 is the 0.07, then we don't care that much of about this feature. So these what are the features we have to give the priority, and what are the features we may ignore, it can be decided by these weights. Okay, this weights is simply if you have a synaptic connections. I said there is a cell body, and like this there are dendrites, okay, some inputs. So this is another cell body, it's axon terminal. This, from the axon terminal there are some of the outputs. So this output will combine with this input. So there itself here electrical signal is converted into the chemical signals there are called as a receptors. Receptors will receive the signals. The strength of the receptors will decide the W1, that is the weights. Okay, then from here these weights along with the proper input, it is multiplied, x1 multiplied with W1. So here my concern is so only how W1 and W2 will decide the values means in biological terms it's due to the receptors in between the synaptics of different neurons. Okay, so here, and another one is the bias. So what is mean by bias means bias is the additional parameter. Okay, bias is the additional parameter in each neuron output, in each neuron that allows the activation function to shift its output curve independent of its input data. Sometimes what will happen, sometimes your inputs are 0, but outputs we may guess something. Then at that time, if we want to increase the level or increase the, let us take one example. So that input data is the example 1, 2, 3, and expected output is 3, 5, 7 for the following input data. And the function we may write y is equal to some ax plus b. So if I am giving, if I want to find that the relationship between these two is the like this. Okay, so here a we may give a equal to 2 and b equal to 1. If there is no bias, we cannot predict, we cannot make the good relationship between the input and output. Okay, if there is no bias, y equal to ax only, then if I am giving 1, then it is the 2, but expected output is the 3. If I am giving 2, it's a 4, expected output is it's a 4 will come. Okay, expected output is the 5 and actual output is 4. Like this, there is some deviation from the actual output and predicted output. So if I am combining one biasing term, that is b equal to 1 over here, then for the 2 we are getting 2 plus 1 3, and for the input 2, then 2 multiplied with 2, 4 plus 1 5. Like this we are close to the whatever the expected results. So sometimes this b will shift the output curve to the certain level. So that is the importance of the bias in neural networks. Okay, and this is the architecture of the single neuron. Now come to the different activation functions, because see here it is added x1 is multiplied with w1 plus x2 multiplied with w2 plus b, that is a function has been summed up. Now this activation function will take the decision based on this output. What we have to do? So after taking the decision, it will give a output to the next neuron, or to the, for some application, whatever it is. It may be this output will go to the next neuron, or maybe stand over here only. Okay, so this activation function will play a key role. So here come down to the activation function. I have two types of linear and non-linear activation functions. So first, there are different activation functions we can take. First one is the step function. Simple function used in the regression problems. And second one is the sine function. And third one is the sigmoid function. And fourth one is the Tanh function. And fifth one, final one, is the ReLU function. Okay, these are the most important functions used in the neural network. Apart from this, there are several functions also available, but these functions we can discuss today. Okay, first one, coming to the step function. Step function. Okay, if I'm look at this graph, this step function is like this. Like this. Okay, so the function, if I am writing some f of x equal to 1 if x greater than or equal to 0, and 0 if x less than 0. Okay, it is suitable for binary classification. Okay, it's a simply linear, because the problem is that it has some discontinuity at 0. So if there is a discontinuity, then the derivative will not exist. So that's why we cannot apply these for the non-linear functions. So that is a demerit of this step function, but it is remaining is very good advantages if I am taking step function. And it's simple for the simple problems. It will give the better outputs without any complexity. Okay, so that means if the input is greater than 1, greater than 0, it will give you a 1. If it is less than 0, it will give you a 0. Okay, this is a step function. And another one is the signum function. It is also called as a sine function. Okay, it is also called as a sine function. So here we can take that function is the sine of x. Okay, there are three categories, that is the three phases. -1 if x less than 0, 0 if x equal to 0, 1 if x greater than 0. There are three categories. So here same way, if it is input is greater than 0, then it is give the output as a 1. If it is less than 0, if it is give the output as a -1. If it is x equal to 0, then here itself also at x equal to 0 we have a discontinuity. So this can also not suitable for the non-linear applications. So still we have not used any, but most of the practical cases it is non-linearity is there. So most of the problems will be dealing with the non-linearity. These two functions, it is not suitable when we are dealing with the non-linear functions, non-linear applications. Okay, non-linear applications. This can be suitable for the some binary classifications, linear classification problems. So there is a simple activation functions, and it can process very quickly also. So, and now next one is the third activation function is the sigmoid activation function. Sigmoid activation function. So the formula for this one, it is the 1 by 1 plus e to the power of minus x. Okay, here the range of the sigmoid function is the 0 to 1. So here one more, the advantage of the sigmoid function is it is introducing non-linearity. Okay, introducing non-linearity and enable to learn complex problems. Okay, enable to learn complex pattern or problems. Okay, so here there is no discontinuity at x equal to 0. If I'm look at this graph, it is a 0 to 1 means it is looking like this. Okay, this is the middle point is a 0.5, this is 1 and this one is 0. So it is graph is completely continuous, so therefore it can be used in the non-linear applications. And another one is the tan h function. Okay, so for the function tan h of x is equal to simple e power x minus e power minus x by e power x plus e power minus x. So here this one also can be used for the non-linearity applications. This is a one more activation function, and final activation function is the ReLU activation function, is also called as a it's a rectified linear unit. Okay, this one rectified linear unit. Coming to this function, it is a f of x equal to x when x greater than 0 and 0 when x less than or equal to 0. So this will give you output like this. So here ReLU function is mostly used in non-linear applications in recent days. Okay, it cannot bounded to the certain outputs. It can increase up to the increase. It depends on the x values. Okay, so here these are the 5 activation functions. Among this one, I said already, sigmoid, tan h and ReLU functions can be used for non-linear applications along with the linear, and this step function and sigma function is only used for the linear applications because it have a discontinuities at x equal to 0, but remaining there is no discontinuity. That's why it can be useful for the non-linear applications. So let us go with the one problem, that is here they have given the one two inputs, that is x1 is equal to 1 and x2, there are two inputs, it's a minus 2, and associated weights also they have given. W1 is equal to 0.5 and W2 equal to 1, and they are given the bias is a 0.5. They are asking to implement this single neuron, single perceptron neuron with the 5 activation functions. So let us take, then I am drawing this architecture, that is x1 and x2, and this one is the some y and this activation function. So y I am taking over here, and bias is the 0.5 and W1 is the 0.5 and W2 is the 1. So our formula, we know that the y equal to x1 W1 plus x2 W2 plus b. Okay, so this one is a x1 is a 1 multiplied with 0.5 plus minus 2 multiplied with, sorry, here W2 is 1, right? Is a 1 plus 0.5. So this will give you the y equal to minus 1, right? Now that at here the output is the summation, the neuron has received the information is minus 1. Now activation, different activations, how it can behave with this input and what are the outputs will be getting by using these activation functions. Let us check. First one is the your step function. What is the step function formula? Simply, if input is greater than or equal to 0, f of x is equal to 1 when y greater than or equal to 0 and 0 when y equal to less than 0. Okay, so then this will give you that's y equal to minus 1. So obviously the output is 0. Okay, output is equal to 0 from this one here. And next come down to the, this is f of y, okay, f of y, sine function. So what is the, that's f of y, we can take 1 when y greater than 0, 0 when y equal to 0, minus 1 when y less than 0. Obviously y equal to 1 minus 1, so it is less than 0, then your f of y is the minus 1. Okay, now next one is the sigmoid function. Sigmoid function. Okay, this sigmoid function, what is the formula? 1 by 1 plus e to the power of minus y, f of y equal to, so y here it is a y equal to minus 1, so therefore 1 by 1 plus e stands for 2.718, right? So this will give you the answer. So already I have calculated 0.268. This is the activation function output if I am using sigmoid. And another one is the tan h function. Okay, so here after substituting this one directly, I am writing f of y is equal to tan h of minus 1 will come. This will give you minus 0.712, right? And another activation function is the ReLU function. ReLU function, it is the f of y is equal to y when y greater than 0 and 0 when y less than or equal to 0. So here automatically your output is less than or equal to 0, then f of y is equal to 0. So these are the different outputs in case of if we are using different activation functions. So these activation functions are, we have to use according to the certain applications. First, if you know the application, you can choose. If it is a non-linear application, the ReLU function is a recommended function because it will give you the almost a close outputs as compared to the remaining. That's why in most of the research papers or most of the applications, ReLU function will be used. Okay, here if you observe, it is not a y, it's a sorry, not a 1, it's a y. That means whatever the input that can be followed if it is greater than, simply right, I said this is the function. Okay, it depends on the input. You are giving how much weight, weight updating. While weight is updated, this function can be used. Okay, these are the 5 activation functions and their outputs. Step function, it is the, if I'm writing step, it is a 0, our output, and sine function is minus 1. If I'm using sine function, it is minus 1. And next one is the sigmoid function. If I'm using 0.268, sigmoid 0.268, and tan h, it is a minus 0.712. If it is a ReLU, then it will give you the 0. So like this. Okay, this box is connected to this one. Activation function over here, right? These are the outputs. Okay, if I am using different activation functions, we are getting different outputs. So this will depends on the how completely purely application based. Okay, next one is the loss functions. Okay, we are predicting something. Okay, whether we are getting perfect results or not, that can be predicted by using some loss functions. I am predicting just whatever we have discussed here. If I am predicting 3, sorry, if that actual is 3, my predicted output is 2, automatically there is an error. So this error is most important in the practical applications. We have to reduce this error by using different formulas, and we have to take the appropriate weights to reduce this output. How we can calculate it means the most used error functions are loss functions. It's a mean square error. Okay, and another one is a mean absolute error. and some other errors also. Root mean square error, mean another one is the maximum absolute error, and normalized maximum absolute error, normalized mean square error, normalized mean absolute error. Like this, different errors are available, but these two mostly they will use in practical calculations. If your data is outlier, okay, in the neural network or in your machine learning algorithms, if your data is outlier, then go to the mean absolute error. If data is within a within a domain, then you can choose the mean square error, because if the data is outlier, squaring means it will give very large difference. That's why MSE is not recommended if the data, sum of the data points at outlier. Okay, so here if I am coming to this one, the formula for this mean square error is a 1 by n summation of equal to 1 to n yi minus y cap I square, and here it is simply 1 by n summation of I equal to 1 to n absolute value of yi minus yi predicted. This is I, not 1. Okay, so how we can remember this mean square error, mean absolute error means? First we need to error, so this is the error. Okay, next one is you have to square, I made a square, and finally you performed a mean. So mean is the sum by total number of samples. Same here itself also error is there, and absolute value, okay, absolute we have to consider, then find the mean. So these two are the most important error terms to check whether the our predicted model is how much accurately getting the results. Okay, this if the mean square error is very small, then that means we are going towards the practical outputs. Okay, that means we are reaching towards the perfect results. If mean square error is very large, that means our predicted model is not exactly tracking the outputs. So therefore we need to change our weights. By changing the weights, that is called as a this term now, right, this is a feed forward network. There is no feedback over here. Remember, this one is the feed forward. It's complete architecture. If I am taking feed forward network only, there is no feedback. If I am giving feedback, then there is a concept of back propagation will come. Okay, this concept of back propagation will come, and we need to change that is we need to update the weights by using back propagation. There itself there is a utilization of gradient descent algorithms will be performed. The gradient descent algorithms will be performed their mathematical functions to change these weights. Okay, this is the introduction to the artificial neural network. Here only I have taken the single neuron. Okay, and there I have introduced 5 activation functions and their importance, and where we can use these things, and finally we came to the loss functions, mean square error and mean absolute error. So this is the end of the introduction of artificial neural network. Thank you all. If you like the video, please click on the like button. Thank you.